Hello, my name is Krzysztof Hojnowski and I am a senior support engineer at SOMLabs. Today's meeting is the third in a series of webinars dedicated to the Yocto NXP system and the SOMLabs VisionSOM modules. This time we will run the program on the Cortex-M4 core and communicate between the real-time Cortex-M4 and application A53 cores. At the beginning, we will turn on the support of the M4 core and set up the communication channel between it and the A53 cores in the device tree. Then we will move on to discuss domains and the division of access to the processor peripherals between individual cores. Finally, we will learn how to download the SDK for the application on Cortex-M4 and how to compile and run the sample application. As before, we will also do some practical exercises this time. At the beginning, we will build a new system image after applying the prepared patches that launch Cortex-M4, and we will launch the application intended for this core. Finally, we will prepare a system image in which the application will be launched automatically at system startup. The necessary resources for all exercises are in the Home Dev Exercises Workshop 3 directory on the virtual machines disk. We will start by adding support for communication with M4 in the Linux device tree. This communication takes place with the use of shared memory in the form of so-called mailboxes. However, from the Linux user's point of view, it is an ordinary serial port to which we can write and from which we can read data. The shared memory is configured in the patch 0001 added support for Cortex-M4 rpmsg patch added to the file list in Linux I.MX8M append. The patches from the previous exercise with modifying interfaces in the device tree have been removed due to the fact that the UART3 used before will be assigned for exclusive access by Cortex-M4 this time. In the mentioned patch file, 3 new sections were added. The I.MX8M CM4, rpmsg, and the memory blocks required by these peripherals. In the I.MX8M CM4 section, a compatible device is defined, which is of course a Cortex-M4 with the within the I.MX8M, and the mailbox is used by it. Memory area definitions omitted on the slides are also included in the patch file that I encourage you to check. Details about the individual fields and the exact configuration of the device can be found in the documentation distributed with the Linux sources. The file describing this device is imx.rproc.yaml. Another section added to the device tree is rpmsg, which defines the virtual serial port used from the user space for intercore communication. Its fields include the number of virtual devices, the memory definition for storing descriptors, shared memory space, and of course the status enabling this device as in the case of other device tree sections. We can now copy the patches and the new BB append file to the Linux I.MX recipe as we did before, but before rebuilding the image we will modify the peripheral allocation to the domains. Peripheral access management is performed by RDC, so Resource Domain Controller. It enables the allocation of the core, for example Cortex-M4, to a separate domain than the Cortex-A53 cores. Together with the core, we can assign selected peripherals to the same domain, thanks to which he will have exclusive access to them. And attempts to access them from the context of the application cores, so from the Linux system, will end with an exception. We can also establish shared access, thanks to which all applications, regardless of where they are executed, will have access to the given address space. RDC configuration is performed by the ARM Trusted Firmware module code. It is started before the U-boot and the system. The recipe that builds this component is called I.MX8M. By default, all peripherals and cores are assigned to domain 0. The change to this assignment was made by patch 0002 assign M4 and UART3 to domain 1 patch located in the exercises workshop 3 lab 1 directory along with the modified ATF I.MX recipe bb-append file. When browsing the patch, we find the writing some values to RDC registers. The first line assigns Cortex-M4 to domain 1, and the second one blocks access to UART3 from domain 0, so the one where the application cores are located. Let's take a moment to explain where these addresses come from and what the entered values mean. The description of the RDC registers can be found in the processor's manual in table 3.2. It informs us that the Cortex-M4 configuration is in the RDC MDA1 register, which in the memory map is at the address 303D0204. Hence the patch contains the entry I.MX RDC base plus 204. Because the RDC register address base is equal to 303D0000. In the register description, where its fields are explained, we can see that writing 1 to the least significant bit assigns the core to domain 1. Let's analyze the second record, writing values FC to the address I.MX RDC base 5A0. In the table 3.3 of the manual, we can see that the configuration of the UART3 domain is in the RDC PDAP104 register, which in turn is at the address 303D05A0. In this register, the least significant byte determines read and write access to each domain. Therefore, entering the value FC disables access to this peripheral for domain 0 completely. Let's copy the patch to the ATF I.MX recipe. With the kernel and ATF modified, we can build a new version of the image, as it was discussed in the first part of the workshop. So far we've only been working with Linux, but now we're going to discuss how to build applications for the Cortex-M4 core. At the beginning we will need a separate SDK containing, among others, peripheral drivers and free RTOS. The ready-to-use SDK with an application example for I.MX8M added is located on the virtual machine in the Exercises Workshop 3 Lab 2 directory. The official version of the SDK from NXP can be downloaded from MCU-Expresso NXP.com. Click on Select Development Board, select the processor we are interested in and click the Build MCU-Expresso SDK. Before we find the right package, however, we need to know which SDK version is suitable for our Yocto. We can find it by looking inside the I.MX Yocto BSP sources Meta I.MX, Meta SDK, receipts, FSL, M4 demos, README file. From it, we learn that in the case of our Yocto, the SDK version 2.6.1 is suitable and it should be downloaded from the NXP site. So we enter the version number, select all the components we want in the SDK and click Download SDK to download the archive with the necessary libraries. With the SDK downloaded, we can look at how to build an application on Cortex-M4. Let's go to the directory with the example Exercises Workshop 3 Lab 2 and set the necessary environment variables using the set and sh script. This script sets the armgcc dir variable and completes the path variable with the directory where the GCC ARM non-ABI cross-compiler is located. This compiler is already placed in the virtual machine, but it can also be downloaded from the developer ARM.com website. Then we go to the directory with the application example. This example is a modified version of the NXP application for the EVK-M I.MX8M board. The used UART port for printing diagnostic messages has been changed, and the LED control with incoming commands has been added, which we will test in the next step. All examples contain build scripts that we can run as needed. See the documentation available to download with the SDK from NXP website for details. We will use the build debug script, which is in the ARM GCC directory, inside the directory with the example. So boards, Vision SOM 8mm, multi-core examples, RPMSG, Lite, STR, Echo, RTOS, ARM GCC. There we call the build debug script and wait for the compilation results. Having the binary, we need to copy it to the target system's boot partition. After booting Linux, it is mounted in the run media mmcblk2p1 directory. There is also the kernel file and compiled device tree located. The binary file for M4 can be copied directly from the virtual machine using the scp command shown, if we connect the Vision SOM board to the local network. When the binary file is already in the device memory, we can run it on the Cortex-M4 core. Before starting, you can also connect the UART USB converter to the UART3 port, as in the previous section, while modifying the device tree for UART3. It will display the messages sent by Cortex-M4 application, but this step is not necessary. Let's connect to the serial terminal, so J-Link console socket using a micro USB cable. Next, let's reset the device so that we can see the U-boot logs in the terminal. When hit any key to stop auto boot message appears, press any button to stop the booting process and go to the U-boot console. Unfortunately, the loading the application on the Cortex-M4 is not a trivial thing and requires entering a few commands that load the application. Using the fatload mmc and cp.b commands, we will load the binary file from the SD card or the eMMC memory and copy it to the RAM memory to the address from where it can be executed by Cortex-M4. The copied file can be run with the boot aux command with the appropriate address to which we copied the binary file just now. After this, the boot command will resume loading the Linux system. The Cortex-M4 application initializes the RPMSG on its side and then waits for it to be loaded on the application core side. Then it starts waiting for incoming messages. The application status can be observed through the logs on the UART3 port. To be able to send data from the Linux user space, we must first load the I.MX RPMSG TTY module, with the mode probe command after logging as root. This module creates a new device, dev tty rpmsg30. If we send the text on to this port, then the program on Cortex-M4 will light on the IO4 diode on the carrier board. The string off turns the LED off. In addition, we can confirm the availability of the GPIO through both domains. The IO4 diode can also be controlled from the Linux file system via the file sysclass LEDs and then brightness file. Finally, we will introduce some changes so that loading the binary for Cortex-M4 is done automatically at system startup and does not require manual typing of a large amount of problematic commands. This time we will modify the U-boot code according to the sources that can be found in the exercises workshop 3 lab 3 directory. We can install patches as in the case of the Linux I.MX recipe before. First, let's take a look at U-boot I.MX8M BB append, which extends U-boot's base recipe. In these files, two files have been added to the source list. The first is M4 bin, which is the application binary file for Cortex-M4 built with the SDK. It is the same application as in the previous example, only with a changed file name. The second file is the patch 0001 added loading M4 binary to boot command patch, which we will analyze in a moment. Another change in BB append is the do install append VisionSOM8mm CB procedure. This ensures that the M4 bin file is copied to the deploy directory when the bitbake image is being built. Thanks to this, after installing the image in eMMC or SD card memory, the binary file will be located on the appropriate partition. To run the M4 application in the previous example, we had to enter a series of commands in the U-boot console. This process is automated by the patch added loading M4 binary to boot command patch. It creates the load M4 bin environment variable in the U-boot environment, which contains all of these commands, identical to the ones entered manually in the previous example. They will be run while executing other commands contained in the MMC boot variable. The last file that is in the exercises workshop 3 lab 3 directory is VisionSOM8M Inc. This is a modified definition of the VisionSOM8M machine. It has changed the image boot files variable, which stores the files copied to the boot partitions during the system image build. Now, in addition to the kernel and the DTB file with the compiled device tree, there will be also a binary for Cortex-M4, so the M4 bin file. Everything will be done automatically during system build. The files should be copied as indicated on the slide, so U-boot I.MX BB append to the U-boot recipe along with the patch and binary file. And the VisionSOM8M CB Inc file to the machine description directory, so metasomlabs conf machine include. After making changes, once again we can build and install the new version of the image on the device. After the U-boot logs appear, we can once again stop in its console and verify that the environmental variables introduced in the patch are visible. With the env print we can see the whole list of variables, including the new load M4 bin and the modified MMC boot variables. After the next reset, this time without interruption, the application on Cortex-M4 will be started automatically, as we can see by observing the logs appearing on the UART3 port. After booting the system, we need to log in as root, load the I.MX8M module with mode probe, and send the string on to the port dev tty rpmsg30 to turn on the LED. We can turn it off by sending the off string to the same port. Logs on the UART3 port inform us about the correct execution of all operations. This exercise ends the third part of the workshop series. During the next meeting, we will learn how to access the device using a web application. Thank you very much for your attention.